Excellent. All right. Thank you. Thank you, everyone, and thank you for having me. You've heard a lot about the objectives and how those feed into building an architecture that can help us accomplish our science objectives on the surface of the moon and in the lunar vicinity. So I'm going to talk a little bit more about that translation process. So if we go to the next chart, we as Jake talked about, we define our Mars science objectives. We're driven, or Moon to Mars science objectives. We're driven by the science. That's one of the pillars for why we're exploring. And of course, from the Science Mission Directorate, that's what we're here to champion for exploration. And we start with the community. We want to hear from you, the science community, on what those objectives would be to help us plot out how we want to strategically address all of these objectives going forward. So we go primarily to the decadal reports from each of the science divisions across SMD and update as we need to with those upcoming documents. So of course, the heliophysics decadal is coming out later this year. We're very excited to see what the community is prioritizing for heliophysics, solar and space physics. Planetary science came out I guess, goodness, a couple years ago now, time flies. Astronomy and astrophysics came out before that, and of course the biological and physical sciences came out last year. So we're using all of these inputs to help us figure out the motivation for why we're going and define and codify those objectives in our Moon to Mars objectives. We also have several upcoming Academy studies that will continue to inform the architecture. We're looking at the high priority science campaigns for human explorers on the surface of Mars, which encompasses all of the science divisions, as well as in SMD, as well as human research. And then we're also looking at key destinations across the moon to address decadal level science objectives with human explorers. And then a more planetary focused one with the South Pole Aitken Basin Sample Return Science Definition Team that's soon to be stood up. And then we have a couple additional planned opportunities coming up later once those are completed, so we can continue to evolve the architecture to achieve our objectives. Next slide, please. So from these documents, we've worked with the science community, with both domestic and academia, as well as industry and international partners to help us define the science objectives. I pulled some examples out here just to kind of highlight them, because we'll talk about how these anchor us for getting to what Senthil and Jake talked about with the architecture. But like looking at the human biological science objectives, wanting to understand the short and long-term exposure to environments, lunar and Mars and deep space, evaluating and validating progressively Earth-independent crew health and performance systems and operations, and then characterizing and evaluating how the interaction of exploration systems and deep space environment affect human health, performance, and human factors. So these are all incredibly important, not only for understanding how humans live and work and react and respond to living and working in deep space, which we haven't visited in over 50 years, but also understanding from a science perspective the biological impacts for what is happening biologically. Can we grow crops to help support our crew, and how do model organisms and human physiology, are those systems impacted by exposure to deep space environment? On the heliophysics side, we're looking at improving our understanding of space weather phenomenon to enable enhanced observations and prediction of the dynamic environment. So that is really important, not only for, again, understanding the environment that we're living and working, but enabling us to explore with crew, with humans farther and farther out into the solar system, and helping them be independent of Earth as we can learn how to predict the dynamic environment of the sun and space weather. HS2 is looking at determining the history of the sun and solar system as recorded in the lunar and Martian regolith, And HS3 is looking at investigating and characterizing fundamental plasma processes, including dust-plasma interactions in various environments. Those two in particular have a lot of cross-correlation with other objectives, both for biological systems, understanding the regolith and where it comes from, how does it change with exposure to the sun and deep space radiation, but also with planetary. So there's a lot of really great synergism across the science objectives and science disciplines that we can merge together to achieve multiple science objectives with humans at the surface of the moon, Mars, and of course in deep space as well. And then, of course, HS4 is improving understanding of the magnetotail and pristine solar wind dynamics in the vicinity of the moon and around Mars. And then our last two that I've pulled out for discussion here are the physics and physical sciences objectives. So conducting astrophysics and fundamental physics on deep space and deep time in the unique radio and quiet environment on the far side of the moon, and then advancing understanding of physical systems and fundamental physics in the unique environments of the moon, Mars, and deep space. So all of these, again, together form the basis on which we go to explore. And we've worked, again, with the science community. These are intended to be very, very high level, broad objectives that we can work over time to incrementally address and ultimately achieve these objectives. But they are architecture-wide, like campaign-wide objectives, not mission-specific objectives. If we go to the next slide, this is just a summary of all of the objectives. You've already seen this, so I'm not going to dwell on this chart, but just showing how many objectives we are tracking. So it's a very complex architecture, complex system, but ultimately we're trying to build an architecture that can support the objectives. So in the next chart, going back to that high level objectives, we have to work on translating what that means. So from a science perspective, we have deep knowledge of all of the investigations, all of the steps, what it means to achieve those objectives, what do we have to accomplish, but they're not written down. And so that is part of this decomposition process. It's really a translation process for taking those objectives and explaining to the architecture and identifying the characteristics and needs for the architecture and the use cases and functions that we've already kind of talked about a little bit, but identifying what those are so that we can actually build hardware, design an architecture that can help us achieve these objectives. I'll just kind of re-highlight because this might be new for a lot of you. So even if we've heard this before, I'm just going to re-highlight what these definitions are for these various cases. And then I'm going to walk through a few examples and then explain how you can get involved with helping us figure this out. So characteristics and needs are features, activities, and capabilities necessary to satisfy the goals and objectives that we're identifying. So features and activities and capabilities, and then those at a high level. So I think of that as kind of the thought process for what do we need to do to accomplish, what are the different activities that we have to do, deploy payloads, long-lived payloads that have long looks at the sun, extended, we need to track the exposure of humans and biological systems from orbit down to the surface, those big picture. What are the steps that we have to, what are the different activities that we have to do to accomplish our objectives? So deploy payloads, collect samples, et cetera. And then the use cases are operations that are executed to produce desired needs and or characteristics. So I think that those as feeding into the ConOps. So those are the operations, the concept of operations that need to happen for us to achieve the objectives, and then the functions are the actions an architecture performs to complete a desired use case. So that's a lot of words. Let's go into the next slide and talk about examples. So this, I'm pulling from heliophysics science for examples of what different types of characteristics and needs you might expect. So for heliophysics, you would want to deploy and operate utilization payloads that monitor real-time space weather on the lunar surface and in deep space, cislunar space, Martian surface. Those are just examples, but for one characteristic need, we need to monitor space weather, deploy instruments to monitor space weather on the lunar surface. Then we also need to deploy those payloads in a way that in some cases enable us to have long looks at the sun. And that's important because that's going to drive out different use cases and different functions of the architecture. So we have to call those specifics out at the characteristics and needs level to help us fulfill that translation or decomposition process. So then we'd go to use cases. We'd want to deploy and operate the payloads like we physically want to do that, like actually operationally deploy the instruments and operate them. And that again goes to the next step. They sound really similar, but there are subtle differences for explaining what the next step down is. So like we need to physically deploy those and operate those payloads on the lunar surface with long-term remote operation. And then going to the next step, like what are the functions that we need the architecture to have in order to do that? So we need to provide power for deployed surface utilization payloads for long durations. We need to provide comm, communication and data exchange between surface and Earth. Like those are going to drive out the different ultimately the different types of things that we need the elements to do, ultimately requirements on those elements once they're allocated and into the implementation stage. So it's this step-by-step process to get down into what do we actually need the architecture to do. So that's the heliophysics example. The next chart, please, goes into the human and biology science. So this is a little different, right? We need to transition the crew from microgravity to partial gravity environments. We need to conduct short duration to mid-duration crew exploration missions on the lunar surface. And for this discussion that we're talking about today, this could include IVA, intravehicular activities to investigate how the crew and biological systems are responding to exposure to deep space environments. So then going to the use cases, we need to transport the crew, transportation of crew between cislunar space and lunar surface, and habitation of assets on the lunar surface for short durations. There are also examples, you see the ... etc. Like we need the long durations as well. And so these are just examples of the use cases that we might encounter for human and biology science. And then again, down to the functions, we need to operate habitation systems. And you can help us explain what that means in discussions today and later today. But in remote mode between crewed missions, as well as while crew are there, and then providing pressurized habitable environment, of course, on the lunar surface for short durations. And then what do we want to be able to do with that habitable environment is what we're here to discuss. Okay, so the next chart, I'll finish up with examples from the physics and physical sciences. So we need, again, kind of going back to deploying and operate astrophysics and fundamental physics. In particular, for at least the first of our objectives, we want to be able to do that on the far side of the moon. That's going to drive different architecture capabilities, and then providing IVA, intravehicular accommodations, such as racks, stowage, power on the surface to enable experiments. And then going on from there, we need to, part of supporting those far side opportunities for that take advantage of that radio quiet zone, we need to preserve that far side environment to ensure scientific data integrity for those investigations. And then have the crew conduct of fundamental physics and astrophysics experiments on the surface. And then we need to enable crew surface EVAs and IVA activities, of course, and providing common data. So the next, if you toggle to the next, the reason I'm going into this in so much detail is that there's an opportunity on the next chart. These are being updated this year. And this is a big part of when a new architecture definition document comes out later this year, early next year for review. We're asking you as the community to help us scrub these down, review these, give us feedback on what these look like and help us improve them. And then also, again, today, as part of this discussion, We want you to help us identify what the needs are for surface habitation, part of that IVA accommodations. What do we want to do with that? What are the science drivers for enabling, for defining what that IVA environment looks like so that we can achieve our objectives? So the next chart, please, is I think my walk-off chart. So this is how you can contribute to Artemis. I've kind of already talked through this chart. But the Lunar Surface Science Workshops, this workshop, Jake mentioned this earlier, this is a very important opportunity for us to get feedback from you to help answer these questions for what do we want to do today with the science habit, what are the science drivers for a habitable environment. We will ultimately from this produce a report, and that report will live at the website that I'm showing up on top. Or it's in the middle, I guess. And you'll be able to see what other discussions we've had in these workshops, but also provide input in the report and ultimately be able to access that in this archive going forward. And then I've already mentioned the architecture definition document will be coming out, and we ask for your inputs there, usually coordinated between analysis groups and handed in a consensus document or feedback comments to the agency so that we can take a look and discuss those comments at the workshop. And then there are also solicitations out for instruments. I wanted to highlight that there's an LTV instruments draft on the street, so upcoming opportunities. Jake mentioned that the Lunar Terrain Vehicle is moving forward, and we have opportunities to put instruments on those that are uniquely or substantially enabled by unpressurized mobility. And those, so if you go to NSPIRE's in the Roses solicitation, it's an F call LTV instruments, and you can see that, and comments are due on that draft September 9th. And we'll try to get that final solicitation out on the streets to take advantage of that opportunity. And then additional solicitations that will be coming up are Artemis 4 deployed instruments and Artemis handheld instruments. All right, I think that's it. Can you go to the next chart? Yes, excellent. So I will close there and join the panel for taking questions at the end.